Hey, this is Horner, and this is the 2018 AP Physics C Mechanics problem. And I like this problem because you have to use integral calculus in order to show the rotational inertia of something. So this is commonly done on the AP test. I know we've done one already like this, but this one's a little bit different, so you'll kind of like this one. So we have a triangular rod, kind of looks like this. It has a length L, has a mass M, capital M, and it is non-uniform. And because it's non-uniform, they've given it a linear mass density. So what does a linear mass density mean? Well, what it means is if I have something that only has one dimension, so we look at this string, then we could say that because its width isn't very big, that we're just going to worry about one dimension here. And they say that the linear mass density is 2m over L squared times x. And so they've just given it an equation for this object. And so what's kind of cool is it's just the mass of the object divided by the length. And so that is the linear density. If you remember, rho is, well, sometimes rho looks a little bit better. It looks like this, is equal to mass divided by volume, and that is volumetric density, or what we refer to as just regular density. So this is linear density. It's just mass divided by unit length. So instead of 3 dimensions, we're really looking at it just in this one dimension. So let's go ahead and start this one. On your equation sheet, you'll notice that you do have an equation that has an integral in it, and for the moment of inertia, and that is I is equal to the integral of r squared dm. And in order to do this one, we don't have an r squared, and so what we're going to do is we're going to look at integrating x squared, since we have x over here, x squared dm. If you do that much, you actually get 1 point. So this much right here, is worth 1 entire point. Let's go ahead and take a look at the next part. So from here, now we need to use this linear density. So we know that the mass of an object, if you think about it, is equal to the integral of the linear density times the change in its length. So really, if we think about just regular density, rho, that's equal to mass over volume. So if I want to know what the mass is, I just take the linear density and I multiply it times the volume. So same thing is happening here. If I know the linear density, and it is mass per unit length, if I want to know what the mass is of this, I just take the linear density times the length. So that's the only reason that we've done this. This is that linear density, and this represents that change in length. So hopefully you're making these type of connections. You're seeing that it's really not that hard. It's just that when you use calculus, it makes it a little bit easier to kind of explain. So now this is equal to the integral of, remember we said that this symbol is equal to 2m over L squared times x. So we're going to put that in. So this is 2 times the mass over the length squared, and we multiply that times x, and then we do dx. So at this point, let's go ahead and let's put some more into this. So we know that I now is equal to, and at this point we need to go ahead and put in our x squared. So we're back to the I equation. So here's our I equation. So it's the integral. So there's our integral of x squared, and then it's dm. So we've got x squared. So let's put in what we have. So we've got 2m over L squared x, and then we multiply that times dx. At this point, we're going to go ahead and do some math here. So we're going to say this is the integral of, and we've got 2m over L squared, and then we're going to multiply that times. So notice x squared times x is going to give me x cubed, dx. And now we're going to turn this into a definite integral, which means that I know I'm going to go from one end to the other end of this object. So the object has a length, and it's represented by x is equal to 0 and x is equal to L. So those are our limits that we have on this. And now we can go ahead and put in our equation again. So that's 2m over L squared times x cubed dx. So now we have our equation. We need to actually do the integration. So let's go ahead and do the integration. So this is I is equal to, so if I do the integration, I'm going to put brackets now around what it is that I end up with. If I have x cubed, I add 1 and then I divide by that number. So I'm going to go ahead, and on this side I have x to the 4th divided by 4th, and I'm going to multiply that by what I did not have to do, and that was I didn't have to worry about doing anything to the 2m over L squared, since that's the constant. We know that we are going from the lower limit is x is equal to 0, and my upper limit is the length. So anywhere I have x, I'm going to substitute in the letter L, and then this would be kind of like your final conditions, and then we're going to subtract our initial conditions. Well, if x is equal to 0, and I put 0 in, then the whole thing is 0. So really I don't need to pay much attention to the x is equal to 0. I really just need to evaluate this for x is equal to L. So let's do that next. This is equal to 2m, and then that's over L squared. We're going to multiply that by, so remember we said x now is L, so this would be L to the 4th, and we divided that by 4. And if you really wanted to be technical, you could say it's minus 0, because if I put 0 in, the whole thing becomes 0. Let's go ahead and let's put all of this together. So now we have 2m L to the 4th all over 4L squared. And I can reduce this down. So I'm going to take the 2 away. This becomes 2 then. And then I can take one of the 2's off the bottom, and then this is squared on the top. So now I get to my final answer, and yes, you do need to write it down. So this is m L squared all divided by 2. Let's go back and figure out where we get points for this. So we got 1 point at the very beginning. You get 1 point for doing the work that we see here. So it's really just going in and setting up the integral so we can integrate. Then once we do the integration and end up with our final answer, we get 1 point. So that beginning part is worth 3 points. And it's a lot of writing, but it's easy to do as long as you kind of know what to do on each part. For the second part, letter B, now we have a thin hoop. So here's our thin hoop. It has a mass m, a radius L, and a rotational inertia around its center of mL squared. They put 3 of the rods inside and they're fastened to the hoop. So really all we've done here is maybe make a high-tech bicycle wheel, which only has 3 spokes on it to reduce weight. They want us to go through now and derive an expression for the rotational inertia. So that's I total of the hoop rod system. So I want to do it for this whole thing about the center of the hoop. So that means right here. So we don't have to do parallel axis theorem. Instead, we just need to know what the sum of the momentum are, sum of the angular momentum. So the sum of I is going to be equal to our I total. So I total here is equal to 3 times the moment of inertia of each rod, which we just found, plus I for the hoop. So one of the cool things, and we'll stop here for just a second, when you look at this problem, you're going to notice that they told you what the rotational inertia of the rod is. So if you don't have time, let's say you only got 5 minutes left and you want to maximize the number of points, doing this integration probably is not going to maximize your points. But because you have this moment of inertia here, you can go ahead and just skip right to this part. Because now we can just say this is equal to 3 times mL squared over 2, so they told us that, And then they also told us I hoop, and it said it is ml squared. And where is that? That is right here. So that much is worth 1 point. So if you recognize you can use your answer from before, which essentially is an answer that they gave you, then you should be set. Now at this point, we're still not done. We need to go ahead and we need to do a little bit more math. So this is going to be 3ml squared all over 2 plus, now we need to multiply this by 2 over 2, and that's 2ml squared over 2. If you add the two together, we end up with 5 halves ml squared. And that is where the second point comes from. So if you left it like this, you'd only get 1 point. If you go ahead and work it all the way down so that you have one thing instead of two, you end up with that second point. So let's go ahead and take a look at the next part. This is part C. And now the hoop rod system is initially at rest and held in place, but it is free to rotate around the center. A constant force is exerted tangent to the hoop for a time t. So essentially what they've done is we have this hoop and they've put a bar or a rod through the middle, and then you've got your spokes that they already kind of showed you that are there. And then they apply a force in this direction, tangentially to it, for a time t. Since they exerted a force times t, we know that they have a torque, and that torque is happening for a period of time. So we're going to multiply. We don't want to divide. I want to take the torque, and the torque is applied for a moment of time, so we can put that times delta t. What's cool about this is this expression is actually equal to the angular momentum of the system. The other equation we have for angular momentum, which is in your equation sheet, is really I times omega, but we are looking at the change. So this is really the change in the angular momentum, hence we have the time. So that's I times the final angular frequency minus the original angular frequency, where 2 is final and 1 is initial. So why is it that this thing is actually equal to the torque times the change in time? Why is that equal to angular momentum? Well, here's why. So in fact, let's do this in a different color. You would not need to do this on the test, but knowing why it is important because they might ask you why. So torque, remember, is just force times radius. Force is mass times acceleration times radius. So this is all linear. Mass times, now we've got acceleration, which is the change in position over the change in time, but it's change in time squared. So really we're just doing a differential equation if you think about what we're doing, but we're not doing it using the calculus. We're just kind of going through and kind of mixing everything down. If I have this now, the other thing I can do is say, well, this is also equal to mass times velocity. Velocity is change of position over change in time, times the radius times 1 over the change in time. So I just took this and I undid it. I took this, made it so that I've got delta t times delta t. And remember, this is your radius right here. So that looks kind of messy, but the question is, why is that L? Why is that the angular momentum? So we know that this is equal to mv r, and that is times 1 over delta t. Okay, so that's what we just said. That's this part, that's the torque, and then we're going to multiply that times the change in time. So if I do that, notice this much is torque, and this much is our change in time. So now that's proven that we have a change in angular momentum can be equal to torque times the change in time. That's something we have not done. So that's a really good thing to make sure that you memorize. And then this kind of shows you how it works. And so that is very, very, very useful. At this point, we can go ahead and set this and this equal to each other. So we're going to say the torque times the change in time is equal to the moment times the change in the angular frequency or the angular speed. And now I want to solve for that change in angular speed. But first, we know that this is force times radius times delta t is equal to I times that change in the angular frequency. So angular frequency is equal to FR delta T all over I. Now, it said to find the angular speed of the hoop rod system, and we did that, but it says express your answer in terms of M. Nope, we don't have that. L. Nope, we don't have that. F. Yeah, we have that. And T. So we really need to find a way to get this to M and L. So let's go ahead and think about that. So this first part is our first point. So there's our first point, number 1. Now let's move this down a little bit, and we could say that omega is also equal to force, and instead of R, remember they wanted us to use L, so we've got that L times delta T all over I. So now that I've substituted it in, so you can kind of see how they're giving points here, they've got these letters, and they want to make sure you have everything in terms of those letters. So the first thing we did was we changed the, well, we got this first, but now we've got L instead of R. Next thing that they probably need us to do is go ahead and solve for that final equation. So we're going to do that here. So now we've got omega is equal to FL delta T over, and remember we said I is 5 over 2 ml squared. So we did that earlier in the problem. We're going to multiply both the top and the bottom by 2/5. So that gets rid of this, and that leaves us with the equation that is the final answer, which is 2/5. The force, and you'll notice that this L crosses off and this one L crosses off here. So this would be F delta T all over M times capital L. And that is your final answer for part C, and that is worth 1 point. So you had 3 points on this part also. Next part seems easy. It should be, but some people mess it up, so we're just going to make sure we have everything correct here. The hoop rod system is rolling without slipping, so we know that there's got to be some friction there. So whenever you see without slipping, just write force of friction. Along a level horizontal surface with an angular speed, at time t0, the system begins to go up a ramp. So right at this point right here, we could say that our time is equal to 0. So when the bottom of this hits right here, that's what's going to happen. So they want us to go through and on our figure, so on this picture, they want us to draw and label the forces, not the components that act on the system. Each force has to be represented by a distinct arrow starting at and pointing away from the point at which the force is exerted on the system. So we're going to make sure that we do that right. I'm going to get rid of that because it might be in the way. And let's go ahead and do this in blue. First one we have is straight down, right from the middle, and that would be mg. So that's your first point. Your next 2 points need to start right here. So I would put a dot, and I'd also put a dot here to show what you're doing. This is going to come straight up through the center, since it's the center of mass, and this is Fn. And then finally we have FF pointing in this direction. Now on the old AP Physics C exam, they would just say, okay, you got your 3 points, you're done. But because AP Physics 1 now has lots of explanations, in order to kind of get you to go through and do this right, they are going to have you justify so they're going to have to justify your choice for the direction. So let's go ahead and do that. We know that Fn, so Fn is always perpendicular, and you could write the sign to the surface. We know that the force of friction for a rotating object is always in the opposite direction of rotation. And then finally, mg is always vertically downward. And so those are the explanations that you would have to have in order to get those 3 points. Okay, so let's take it the very last part. It says derive an expression for the change in height of the center of the hoop from the moment it reaches the bottom of the ramp until the moment it reaches the maximum height. So it's going up the ramp, and we're looking at the center of the hoop. So that would be right here, and then it moves its way up here. And so we are looking at this distance here. So from the center over to the center. So that is what we are looking for, and we're going to call it capital H. Let's go ahead and get rid of that so we have enough room here to put everything. And let's start by saying that we know that the kinetic energy at the bottom should be equal to the potential energy due to gravity at the top. And because we have more than one type of kinetic energy, we need to put both in. So this is 1/2 mv squared plus 1/2 I omega squared. And that is equal to 4 times mgh. Now, why is there a 4 in front of the m? It's because our circle has a mass of m, so our hoop, and then each one of these spokes also has a mass of m. And so because of that, we need to put in 4 for that. In fact, we also need it right here. So it's 1/2 of 4 mv squared plus 1/2 I omega squared is equal to 4 mgh. You get 1 point for having the two kinetic energies separated at this point. Next thing we need to do is go ahead and put everything in. So let's do that. This is 1/2 of 4 times mass. Now, we can't use v here. We can't use v squared. And we do have something that's rotating. So what we're going to do is, for this velocity, we're going to put in L times omega. So L times omega is equal to velocity. So that is another way to think about it. And we need that because L is the length. So here we've got V. Usually we have V is equal to omega R, but for what we're doing is we need to take V and multiply that times that length that we have right here. And so that's why you see it the way that you do, squared. Plus, and now I have 1/2 I, and then this is the total. And it does say that that's what we need. So we're going to use I total times omega squared. And that's equal to 4 times m times g times that height. So at this point, we can reduce some things down. So this is 2ml squared. Oh, by the way, you get a point for recognizing what this is. So that's 1 point, because remember, this is a length. So that's just omega times the length. That makes it a lot easier. So we have 2ml squared omega squared plus 1/2 of I total times omega squared, and that's equal to 4 times m times g times h. So at this point, we're going to divide both sides by 4 mg. So I would do it in both places here instead of just doing one big line. That'll make it a little bit easier. And we can cross some things off. So one of the things we cross off here is mass. This gets crossed off, leaves us with 2. Here, the 2 comes down to the bottom, so that makes this 8. There's nothing else to cross off on this one. And the next thing we need to do is we can get rid of the 4 mg on this side. Okay, now that we've done that, let's go ahead and rewrite it for h. So we know that our final answer here is h is equal to L squared omega squared, so that's top, all divided by 2g, because we got rid of this m, plus, and then we have I total times omega squared, all divided by 8 times m times g, and that is the third point for this. And that is the end of the 2018 mechanics free response question number 3.